Good afternoon, everybody. So it's a pleasure to be here to introduce the speaker for our DI seminar today. So the speaker is going to be Carlangelo Liverani, which is an old friend of the group, and from the University of Roma Vergata. Just before starting, let me remind all of you that the seminar will be registered, and we are also online on YouTube. So you are, of course, welcome to ask questions. You can either ask by yourself, just turning on your microphone, or writing them in the chat, and then I will ask the question to the speaker. And in both cases, if you do it, just remember that you are recorded. So I think it's time to start. So Carlangelo will talk about locating Ruelle-Pollicott resonances, and thank you, Carlangelo.
Well, thanks to you for inviting me. Actually, I'm a little bit, this is kind of my first experience in online seminars, so I don't know, I will manage. I will try not to just use a pad, a graphic tablet to say what I want to say. And yeah, I see that there are a lot of people. You see, this was started as some request to talk about some result that I'm doing with a PhD student of mine, which is Kiamari and Oliver Butterley, that recently joined our department in Rome 2. So I prepared it very informally, but okay, now I see all these people, I'm sorry, I do I do my best. Okay, so what is the story about locating resonances? So the point is that well, just two words. I mean, most of you know.
For the moment, we don't see your screen. Maybe.
Yes, I know. I will share it in a second. You have to bear with my face for a little longer. Yes. No, I wanted to say just a few general word of introduction. That, of course, all of you know, but just to set the stage in case there is some student or someone that is not already an expert in dynamical system. The point is that, of course, dynamical system started, with Poincaré, that essentially pointed out the difficulty of making prediction and crashing, therefore, Laplace dream of, making prediction just giving the initial condition. He just pointed out that solution of a differential equation can be extremely complicated. And okay, that is bad news. And in some sense, it took some time to develop some kind of alternative point of view, showing that something can be salvaged anyhow. And that essentially started with the works of Birkhoff, Neumann, and most of all probably Kolmogorov, that essentially took the point of view that an alternative to look at the evolution of point is to look at the evolution of measures. And that is kind of the framework in which I want to discuss today. So let me just try to share my screen now and see. Now you should see my tablet, hopefully. And so what do I mean by evolution of measure? Well, imagine that you have some dynamical system, let's say topological dynamical system. So you have a topological space X and a map F, or a measurable space even, and a measurable function. Then you can define the push forward of the measure as in the usual way. So the measure of, so this is the push forward measure, and that is the measure of a set A. So this is a set, and it's just the measure of the preimage of the set. So this is okay for any measurable dynamical system. But I will talk about actually, normally in this talk, I will restrict myself to dynamical systems that are smooth or piecewise smooth. So that is the setting that I want to discuss today. Okay, so that is the situation. Of course, the problem in dynamical system is that there are normally a lot of invariant measures. And so if there are a lot of invariant measures, it's not really clear how to find them, how to study them, and so on and so forth. However, you may, very often you are in this situation that you have a measure mu, and you have that the push forward of mu is absolutely continuous with respect to mu. So you can look at the Radon-Nikodym derivative. And let's say that you call this G, for example, okay? And if you are in this situation, then situation is, you can argue, you can define the push forward not only on the measure, but on the density of measures. And how do you do that? Well, imagine that the map F has a partition P, and if P, if you have an element of the partition, F with respect to P is 1, 1. So you can invert it, and so GP, no, G I used it already. Let's call it phi. Let's say phi P is, well, the inverse. So what does this mean? Well, it means that if you take a point, you apply phi P, and then you apply F, then you are back to the point from where you started. Okay, and so then you can look at the measure mu multiplied the characteristic function of P, and you can do the same. You can look at the push forward, and this you call GP. So this is just if you look at the measure of a set A, this just means it is the measure of A intersection P. Okay. So that's what I mean by this way of writing. Actually, in general, I will use the notation that if you have a function, mu of a function is the integral on the space of the function with respect to the measure. So I will use this notation very often because I find it convenient. Yeah, also for me, measures are really functional on continuous functions. So that's why. Okay, so what is the point of having this fact? Well, if you have this fact, it means that you can do the following computation. So you have a measure. So, but what do I mean by this? I mean that you have h of x, phi of fx, mu dx. So essentially, in this notation, you can interpret h as the density of a measure, of a new measure. The measure is mu multiplied by h. And that is a new measure. And now you look at this measure and you look at what is the average of phi compose f. F is the dynamic. And now you can just use the fact that you know that you have this partition. And so you have h of x, and then you have on P only. Okay, but on this guy, you can write actually h of x, you can write it as h, compose h, compose, oh, sorry. H compose f. That's not what I want to write. Compose phi P, compose F, which is exactly the same on P, because you just go with P and then you come back with the inverse, the right inverse. And so this guy here is just essentially what? It is the sum over P, H compose phi P, and then you have phi, everything is composed with F, and then you have the characteristic function of the element P, in mu dx. And so this is a measure, this is exactly the measure I was talking about. So this measure here is the measure mu multiplied by the characteristic function, which was exactly this measure here. Since this is composed with f, this is, you can look at it, this is like saying and then you have the push forward of the measure. It is exactly, I'm sorry, the same thing. Essentially, by definition. And now I assumed that this is absolutely continuous with respect to mu, and the Radon-Nikodym derivative, I called it GP. And so I get sum over P, H compose phi P, GP, and then I get phi, and then I get mu dx. And so you see, now I have that this, if you wanted, it was the push forward. So let me just write this in a different way. I can say that m mu h, this is a measure, and this the measure h d mu. H is the Radon-Nikodym derivative of mu h with respect to mu. So this thing that I had written was nothing else than the push forward of mu h phi. And what I have just computed is that this is exactly this, because this is the measure with density h, and this is phi compose f. If you have to put it on the other side, you get the push forward of the measure applied to the function phi. It's exactly this. And this computation shows that this stuff is just equal to, if you look at the Radon-Nikodym derivative with respect to mu, is just equal to some stuff like that. So this is what people, yes, H, yes. This is what people call a transfer operator. Okay, so essentially the transfer operator is the object that give you the push forward on the densities for a given measure. And there is, it is composed with the preimage of the map. These are the inverse branches. And there is some weight, which is usually called GP, that depend from what measure you are looking at. On the other hand, the thing goes also in the other direction. Imagine that you have an operator of this type. So an operator that looks like, it's a slightly different way of writing it, but is essentially the same thing. Imagine that you have an operator that looks like this. Then, and imagine that you have an eigenvalue of such an operator. Okay. So an important thing of an operator of this type is that you have, this is a right eigenvalue, and also you want a left eigenvalue. A left eigenvalue is something that looks like this. So this is just an eigenvalue on the right, and this is an eigenvalue on the left. This is true for each phi. I'm not being precise about which space I'm talking about, but just I will be precise in a moment. But it's just trying to give the idea for the rare people that never really saw very well a transfer operator or do not realize what it can be used for. So you have such a situation, and an operator of this type has a very interesting property, which is that if you look at, if you apply it to some function h multiplied by a function that depends on phi, a function composed with f, then this is equal to the sum y compose f minus 1 of x, and then you have h of y, and then you have g of y, and then you have phi of f of y. Okay, but f of y is x, just by definition. So this is equal to phi of x, L, this is an x here, of h, x. So it has the property that if you apply the transfer operator to a function that is composed with f, the function simply pops out from the transfer operator. Okay, so now you can, this is a fact, and now you can define, for example, define an object, a linear object of this type. So, of course, this, I mean, in principle, it's not obvious that such a thing is well defined, right? Of course, if this is 1, then it is well defined because this is in some space and this is in the dual of the space because it's just the left eigenvalue which is defined in the dual. So you need that the multiplication by phi doesn't take you out of the space in which you live. But this, if phi is a nice function, normally this is what happens, that you have some h, you multiply by phi, and still you are in the space. So this is in the dual, so this makes sense. Okay, so this defines some linear object. Okay, and now I want to look at phi compose f. So this is equal to L H phi compose f. And now I can use the fact that this is an eigenvalue, so I can write it like this, nu minus 1 L, then, I mean, L dual, okay, then this means that this is nu minus 1 L, L, H, phi compose f. But now I saw that phi compose f, it pops out, so this is equal to minus 1 L, phi, LH, but H is an eigenvalue of eigenvalue nu, so this is L phi H, and this is mu phi. So this object is invariant for the dynamics. If it is a measure, it is an invariant measure. So in general, of course, it's not immediately obvious that it is a measure. In general, it may be something different, but if it is a measure, it is an invariant measure. It's a linear function.
Carlangelo,
yeah?
Please.
Yeah?
We cannot see the bottom.
Ah, you cannot see the bottom?
Yes. Okay.
Is okay?
Okay, okay, thanks.
I'm sorry. Okay, I'll try not to get to the bottom, but unfortunately, yeah, this is, yeah, unfortunately. That is something that I really wonder why. I mean, these people, they do this, you know, graphic tablet, this program, but I mean, this still is confined to the size of a normal page. There is no reason whatsoever why I cannot have a page as big as I want, since after all, it's all electronic, but well, whatever. In any case, so that means that essentially with transfer operator, you can, if you have a measure, you can study invariant measures. So this is the message that I wanted to give you, that you can use transfer operator to study invariant measure, because the spectrum and the eigenvalue and the eigenvector of the transfer operator can be used to construct invariant measure. And on the other hand, if you have a measure and the dynamics is has the property that sends measure absolutely continuous to measure absolutely continuous with respect to this reference measure, then the associated transfer operator can be studied in order to try to construct an invariant measure with respect that is absolutely continuous with respect to these reference measures that you have shown. So that is why it is rather interesting to study transfer operator at the beginning, but then there is much more, because this has to do with invariant measure, but given the invariant measure, you may want to study the mixing, the ergodic property. Is it ergodic? Is it mixing? Now it turned out that being ergodic, it has to do with the fact that the maximal eigenvalue is simple. Being mixing, it has to do with the fact that there is a spectral gap. And so the spectrum of this transfer operator carry information concerning the statistical properties of the system. And normally, if the spectrum is made of, if the spectrum is made of, point spectrum, then the point spectrum are called Ruelle-Pollicott resonances. So the Ruelle-Pollicott resonances are nothing else than the point spectrum of the transfer operator. If you want to see it in this, you can define it independently from the transfer operator, just looking at the Laplace transform of the correlation functions. But from this point of view, they turn out to be exactly the point spectrum of the transfer operator. So with this, at least I managed to explain my title, locating Ruelle-Pollicott resonances. That means that I want to understand the point spectrum of transfer operators. Okay.
Sorry,
so
Carlangelo, excuse me. What is point spectrum?
Point spectrum just means eigenvalue that have finite multiplicity. So you have an eigenvalue, it has an eigenvalue, it has finite multiplicity. It's like a matrix, just like the eigenvalue of a matrix. And these, of course, are operators in general, infinite dimensional operators. So they can have all kinds of complicated essential spectrum, but that is not what I want to discuss.
Okay, thanks.
Yep. So let me just try to start with a very simple situation. So again, there is no general trick to understand what the spectrum of this transfer operator is. This is normally a very difficult problem. What I want to talk about today is a little idea that sometimes gives you information, and I find it kind of surprising that I never saw this idea presented systematically, while I think that probably everybody knows about it, but somehow it never crystallized, seems to me, in a systematic approach. So I would like to try to show that it can be some kind of systematic approach to this problem of finding the spectrum of the transfer operator. And I will try to do it presenting several examples, concrete examples. So let me start with something very concrete, which is a map F from 0, 1 to 0, 1. Okay. Then, and F, I want it to be, well, let's say that I take it to be piecewise C infinity. Just, I mean, you can take it CR piecewise, but just let's take it piecewise C infinity, not to waste any time. Okay, so time is running, so I have to skip something. So let me just look at the transfer operator. I want to introduce a class of transfer operator, which are this one. Okay, so let me also, for simplicity, take the fact that f prime is strictly positive. Okay, I don't want to look at critical point, and I don't want to look at the case in which. So this is strictly positive. That has perfect good sense. And then I take here k, power k, and k is in n. Okay. N union the 0. I don't know if you think that the natural number 0 is a natural number or not. I mean, I don't think it is a natural number, so I put it explicitly. All right. So this is a class. For each k, you have a different operator. Okay. So what? And there is something to be said about this operator. The operator L0. This is the operator that is useful to study the measure of maximal entropy. The operator L1 correspond to measure SRB. So absolutely continuous with respect to Lebesgue in this case. So, and then the other operator, I don't know, they are just other operator, whatever. It's just, they don't have any particular meaning that I am aware of. Okay, and now let me come to this silly idea that I want to explore. And the idea is just to take a derivative, so it's really stupid. I want to take the derivative with respect to x of the operator LKH of x. Okay, so this is the derivative with respect to x, sum y that goes, that belongs to f minus 1 of x, of h y f y prime k. Okay, so if you take this derivative, then what happens? You take the derivative, there are two possibilities. You can take the derivative of this or the derivative of that. These are the two possibilities. If you take the derivative of this, then what are you going to get? You are going to get sum y f minus 1 x, and then you get, if you take the derivative with respect to y, you get h prime of y divided f prime y k. And then, but then you don't have to take the derivative with respect to y. You have to take the derivative with respect to x. And x is f of y. So if you by the derivative of the inverse, you get an extra power in the denominator. Okay. On the other hand, if you take the derivative of the other thing, then you get minus k. You get h of y. You get f prime. Sorry. Y, and then you get k plus 1. And then here you get f second of y. So that will be the derivative with respect to y. But then you have another derivative, which is again the derivative of y with respect to x, that give you another f prime in the denominator. So you get plus 2, something like that. And of course, there is some quantity that is very popular in dynamics, that is the second derivative over the first derivative square. It's called the distortion. And so you get this funny formula that this is the operator Lk plus 1 applied to h prime plus, minus k time, and then you have the operator Lk applied to dh. Okay. So in some sense, when you take the derivative of one operator Lk, you are going to get the operator Lk plus 1 plus something here, which has to do with the distortion. In the case in which, if you take the simple case in which the map is piecewise linear, then the distortion is 0. And then the derivative takes you exactly from Lk to Lk plus 1. Now, this has immediate consequences. So let's say one very quick word on the piecewise linear case. It's stupid, but still. If in the piecewise linear, imagine that you have that L. So first of all, you want to look at what this operator look like. So let's look at let me take L derivative of this operator applied to H, not G. I take the operator Lk, I take L derivative and take the L1 nor, and I compute this. Now, by the previous computation, this is Lk plus L, H, L1 nor, and this is less or equal than the integral of Lk plus L. Sorry, this is the L derivative, of course. L derivative. Okay. And now this one, you can write it in this way, come L K plus L minus 1. And then you have, sorry, that's not what I wanted to write. 1, and then you have HL, and then you have F prime to the power K plus L minus 1. Why? Well, because that's just the definition, no? The definition, you see, you have, where was the definition? Here. So you have K, oops. Sorry. You have K power of the first derivative in the denominator. So you can keep, here you have L minus K power. You keep only L minus K minus 1, and here you have the transfer operator with 1 power. But the transfer operator with 1 power is just, you can just check that it is a contraction in L1. This is something that is easy to check. And so now, if you have that F prime is bigger than lambda, bigger than 1, then this is less or equal than lambda minus K minus L plus 1 of HL. So you see, this operator LK have spectral radius that are kind of small depending on K. So for example, you can decide to look at LK acting on L1. And then the spectral radius on L1 of LK, according to this formula, this is the case in which L is equal to 0, and then it is contained in Z less or equal than lambda minus K, if K is bigger than 0. Okay, so it means that this operator have rather small spectral radius. So you say, okay, so what? Well, so what? Imagine that you have that L1, for example, of H is equal nu H. Then you can take, and imagine, for example, that nu is bigger than lambda minus 1. Then you can take a derivative. You get L2 H prime equal nu H prime. So H prime must be an eigenvalue of L2. But nu, L2 has spectral radius that is lambda minus 1. Nu is too big. There are no eigenvalue over there. So it means that it must be H prime equals 0. Okay? But see, H prime equals 0, you can check. So that means that H is constant. And you can check that it cannot be constant, and then it cannot be an eigenvalue. So it means that the eigenvalue of L1 can be only there can be eigenvalue only, so in this particular case, this will be the case of maps like this, for example, full branched expanding map. In this particular case, you get that the spectrum of L1 seeing in W11, so this is the Sokolov space in which the function is in L1 and the derivative is in L1. This must be something like that. There is 1, of course, and then there is lambda minus 1, and there is nothing else. Because if there is something here, it should be an eigenvalue of L2 in L1, but there are no eigenvalue of L2 in L1, so this cannot be. So this is just some way in which you immediately get a gap in this very stupid example. So let me just, so okay, you say, okay, but this is linear, so what are you talking about? I can do it in bazillion of different ways. Yeah, that's right. So let's look at the nonlinear case. A simple nonlinear case. So let's say, again, to make it simple, some full branch map, but non-linear this time. So this is F, okay? And now, of course, now you have a problem, because if you look at the formulas that I got, this formula here, let's say that I look at the case k equal 1, then you get that the derivative will be L2, but now there is an extra piece, which is this one. Because D is not 0, it's the distortion. So this quantity is not 0, there is a second derivative of the function. So now it's not immediately obvious. You can try to do the same argument, but then you have this operator in the middle. But this operator here is, so let me just do the argument for L1. And then, so imagine that you have L1H, so this is the operator associated to the SRB measure. And now I take the derivative, and I will get L2H minus L1 prime DH equal nu H prime. So you see, it's not an eigenvalue of L2 because there is this extra piece here. But then on the other hand, this one, you can define an operator that is H L star of G equal L2 of G minus L1 D, and here phi of G, where phi of G is the integral from 0 to x of G of G. Okay. But it's not exactly like that because maybe you wanted to have 0 average, so maybe there is a constant that you have to choose properly, but let not me dwell on that. So then what does it mean? It means that this, if you H prime, you call it G, then this equation here becomes L2G minus L1D phi G equal nu of G. And the point now is that, okay, you are looking for eigenvalue not of L2, but of this operator, L2 minus L1D phi. But this guy is compact because this is an integral. So essentially, you are looking for the eigenvalue. I mean, if H is an eigenvalue of L1, G must be an eigenvalue of the operator L2 minus L1 D phi. And this is L2 and this is compact. So still there is some room to try to do something. That is a little bit more complicated, of course, but there is some little room. But the nice thing is that this does not happen for the measure of maximal entropy, because if I look at L0 instead, okay, L0, then the formula that I wrote here, where is it? I lost it. Sorry. This formula here, k is equal to 0. So for L0, it works. So for L0, I have that the derivative with respect to x of L0h is equal to L1 h prime. So there is no distortion because L0 has no potential. So there is no the distortion term. So it means that if I have that L0h is equal nu h, this must imply that L1 h prime is equal to nu h prime. And this, in the case of, for example, this type of map, implies now, what is the spectral radius of L1? Well, L1 H, or let's say G, in L1 is less or equal than the norm of G in L1. So it means that nu must be smaller than 1 or equal than 1, or h prime must be equal to 0. But if h prime is equal to 0, then h is equal to a constant. But if you apply L0 to a constant, 1, for example, this is just the sum on the y that belong to f minus 1 of x. of, of 1. So this is just the number. So if here these are n branches, so this is just n, the number of the branches. So it means that if it is constant, then it is exactly an eigenvalue, must be the eigenvalue n, which is the maximal eigenvalue, because this is equal to e to the logarithm of n 1 times 1, and logarithm of n for that map is exactly the topological entropy. So it means that for such maps, for monotone full branch map, you have that the spectrum of in W11 of L0 is equal to n, and then you have 1. And so you have a rather huge spectral gap. There is nothing here apart from this kind of large spectral gap. And that is kind of, I don't know, I mean, I was kind of surprised because I didn't know this, I don't know, in the literature. In particular, this, I used only the fact, in this case, that the map are monotone and full branched. So they could even have, they don't even need to be expanding. They didn't use the fact that they are expanding. So they could have fixed point, right? For example, it could be that the map looks like this. This is the diagonal. So this is an attractive fixed point. Still, there is a measure of maximal entropy. The measure of the maximal entropy is always n. And the fact that you have this gap, it means that you can construct with the trick that I explained before the measure of maximal entropy. Let me call it Bm for Bowen-Margulis. And then you will have that the integral of phi compose Fn times G in dBm minus phi dBm G dBm. This stuff here is less or equal than what? Well, I mean, the gap. So this is going to be some constant n to the minus n time phi L1 of mu Bm, and then you will have G W11. So you get an explicit that measure of maximal entropy, they mixed kind of rather fast, which, as far as I know, the only results that I knew were for expanding maps that were with maybe with neutral fixed point. There, you know, it was known that they mixed exponentially fast, but it was not known that the gap is this big. And on the other hand, in that particular case, if you take map that expand, but maybe they have some point in which the derivative is 1, so they are intermittent map, like Pomont-Manville map, then in that case, you can prove that the measure of maximal entropy is unique. Here, if you have a fixed point that are attracting, then I'm not so sure that the measure of maximal entropy is unique. But given any measure of maximal entropy, they will because I mean, is unique the measure that is associated to the operator L0, but I'm not sure that maybe there is some kind of weird operator that also gives another measure of maximal entropy. Okay, so that is, time is.
Can I just ask, maybe I lost something, but so are you assuming that the measure of maximal entropy has some kind of regularity?
No, this is just, it comes out that in this case, it is no, what kind of regularity it has? I don't know, because the density is in W11, but the measure you construct it with the So wait a sec. Yeah, the density is 1, but the measure is in the dual. So the dual is.
I was talking about the density.
But the density with respect to what? You want the conformal measure. The conformal measure is the measure of maximal entropy in this case, because the operator L0 has 1 as eigenvalue. So this is the density. Density is 1. This is completely trivial, but the other one is, okay, this is also, and this is the left eigenvalue, and that gives you the measure of maximal entropy, essentially. And this, in principle, the way I'm doing it, it is an element in the dual of W11. So it's not even a priori a measure, it's just a distribution in the dual of W11, but it's not so difficult to show that in fact it's a measure. And so, but you don't get any information on the regularity, just it is some measure. Yeah.
Liverani,
I'm sorry, I didn't.
Excuse me. You know that, please. Lazotte-Yorke is an old fashion because you are not talking about it. Usually when you talk about the spectral gap and the decay of correlations, you study the Lazotte-Yorke inequality, no?
Yes, yes. This is similar to Lazotte-Yorke inequality.
Okay, and
you have to use, here actually I'm cheating, you have to use the Lazotte-Yorke inequality to show that this area, there is no essential spectrum, okay? Because this argument that I did uses the fact that there is an eigenvalue. So if it is essential spectrum, you cannot do it. So you have to use the Lazotte-Yorke inequality to show that I'm glissing on that. I mean, I'm not.
Okay.
Yeah.
Thanks.
Yeah.
Okay. Thank you.
I don't know, because I didn't ask actually how much time do I have? It's just 1 hour or what?
Yeah, 10 minutes more or less.
Okay, okay. So I have to rush up. I took much longer than I thought. So let me just discuss a map F from the torus to itself. Yeah, doesn't matter that it's the torus. Let's M, okay, Anosov. And let's say to make it easy, let's say that the dimension of M is 2, just to make it easy. Okay, now, so I want to see if I can do something similar for maps of the torus, okay, or for Anosov maps. Let me just do the case two-dimensional. Anosov map on a two-dimensional manifold that we know that is a torus, but it doesn't matter that it's a torus. It's kind of. Now, I mean, I want to look at the transfer operator. The transfer operator, I have to decide what this transfer operator is. And, okay, so the problem is the following. Now, I have a contracting direction, okay? In general, the problem is that the contracting direction is not smooth, it's only older. So you see here, what did I do? I took a derivative, right? And the derivative was in the unstable direction. So maybe I want to take a derivative also in the unstable direction in this case. But if I try to do that, I will be into a lot of trouble because the derivative, the vector field is not smooth. So it's not immediately clear how to upgrade this idea of taking derivative and playing this game in the case of hyperbolic maps. But there is a possibility, and the possibility means there are many possibilities, but I mean, let me just talk about one possibility that is kind of, I think it's kind of cute. The idea is that instead of looking at the action on function, you can look at the action on forms, okay? So you have a form, so omega, this let's say is an L differential form. So it could be, for example, and then you look at the push forward. So for example, if omega is a 0 form, what is a 0 form? It's just a function. If it is a 0 form, then this is just a function, and the definition is simply the composition with the inverse. Okay. If omega is a 1 form, so in this case, what would be? I mean, the 1 form, it would be something like omega is equal to some alpha of x, alpha 1 dx1 plus alpha 2 dx2. In this case, the push forward is going to be given by, so this would be just the derivative of f minus 1 applied to the vector alpha 1, alpha 2. Sorry, alpha 1, alpha 2, but I want it, so this would be, if you compute it at the point x, this will be x, this will be applied to the vector alpha 1 compose f minus 1 of x, alpha 2 compose f minus 1 of x, okay, and this time dx1, dx2. This is, I mean, if I write it as a scalar product, it will look like this. So this is just the way in which you push forward. If you have a 2 form, this is 1 form. If you have a 2 form is just something like alpha dx1, dx2. And then if you look at the push forward of that, you discover that this is just alpha compose f minus 1 divided the determinant of df, actually it's better write it like this, time the determinant of df minus 1 omega. This is just, sorry, dx1, dx2, okay? So it means that for 2 form, you have that the action is simply, you have essentially this is 2 form is a volume. This is the density, and the density you act with something that is exactly the usual transfer operator. So you have some way of inducing an action on forms, okay? And what is the nice fact about inducing an action of form is that now you can use the external derivative, because the external derivative has the very nice property that commutes with the action on forms. Okay? And then you have to look at what is the... so now the point is that the action on 2 form has to do with the SRB measure. The action on 1 form of 0 form has to do with the composition, and with the action on 1 form, it has to do with the measure of maximal entropy. That is how the situation works out in this case. And the spectrum, now there are right spaces, there are Banach spaces that you can introduce, and the spectrum of F, so let me say 0 is the 0 form. The spectrum of this on 0 form is contained in z less or equals than 1, and also the spectrum on 2 form is contained on z less or equals than 1. Why this? Well, because these are like the operator that we were looking before at, the operator that have to do with the transfer operator associated to SRB measure, and they are contraction normally, they do not increase. This operator here instead it contains the action of the derivative of the map applying to a vector, so it will increase in general. So this guy will be the spectrum on form. This is going to be less or equal than E to the topological entropy. That is what happens. And now you want to understand if you can understand something about what's going on here. And again, you can play the same game than before. You can say, okay, let's say that I have a 1-4. And let's say that this is an eigenvalue. Then I can apply the derivative. This is equal to f d omega. And now, if nu is bigger than 1, again, it cannot be in the spectrum. So this now is a 2-form. But 2-form, the action of f star on 2-form is as a spectral radius 1. So there cannot be something. So it must be that d omega is 0. So it means that, or more in general, if nu is not in the spectrum for 2-form of f star, then d omega must be 0. So it means that the form must be closed. On the other hand, if you have that a form is, a form is exact, so it is the derivative of something, then if you apply f star, since this commute, it means that also that is exact. So it means that the action on forms preserve closed form and the exact forms. And this means that you can quotient it and you can look at the action on the equivalence classes. Okay, so this one is the action in cohomology of the map. So you can look at the action on cohomology of the map, that is a purely topological thing. And then you can ask yourself, are there eigenvalue? And if here there is an eigenvalue, then this eigenvalue must show up in the spectrum of f star. So essentially, this argument shows that the spectrum of the action on cohomology must appear in the spectrum of the action on 1-4. And in particular implies that the spectrum must contain E, so the spectrum of on 1-form of f star, this guy must contain E to h top, because E to the h top is an eigenvalue of the action in cohomology. And so the spectrum, the conclusion that you get is again the same, which is a result that has been proved recently by Vivian Baladi and also by Forni, but with completely different method. You get that the spectrum of this guy looks like this. And again, you have a huge gap. So there are no eigenvalue outside the circle of radius 1 for the action of this guy on force, which means that the measure of maximal entropy mixes at a speed that is e to the minus h to the topological entropy. So, and the interesting fact is that this way of arguing seems to give a relation between the eigenvalue of the transfer of the action on forms to some topological object, which are the action on the cohomology class, or if you want, since by Poincaré duality, the action on homology. So, which is purely topological. It has, everything about the transfer operator is analysis, right? You look at the transfer operator, you look how it acts on certain function, what is the regularity, and so on and so forth. But then you discover that the spectrum carries purely topological information. So that's kind of, sorry, I mean, it was very sketchy because, I mean, it takes a little bit more to enter in all the detail, but I hope that I gave you some vague idea of, I mean, of this fact that if you can somehow find some kind of differentiation that commute or almost commute with the transfer operator, out of this you can squeeze a lot of information about the spectrum. And in particular, you get some non-trivial information about the spectrum that has to do with the measure, with the transfer operator associated to the measure of maximal entropy. Well, I stop here. I went over time. I'm sorry.
Let's thank Carlangelo. Then, are there questions or comments?
I ask a question. Hi, this is Francesco. In your setup, the power k, the inverse temperature, doesn't really have to be integer, right?
Well, the point is that you see, let me go back.
Do you use the fact that it is integer?
No, of course not. You can put whatever you have. You see, where was it? Here. See, if here you have this computation, you can redo it with any potential. You put some potential here, you take the derivative, and you will get a potential that has one more inverse power of f minus 1, f prime, and then there will be some that has to do with the derivative of the potential, some distortion, some term that has the derivative of the potential. So
you could imagine, instead of doing one derivative, you could do a fractional amount of derivative.
That's possible, but the point is that I'm not sure that it commutes nicely with the transfer operator. This you have to compute.
So in principle, you could do a fractional derivative there, which could perhaps even be used in the case of differentiation in the unstable direction in the case of anodes of flows, if you have a low enough amount of differentiation. But the question is, does it actually behave nicely in terms of commuting? And it's not clear.
That's possible. For anodes of flows, if you don't want to look at the action on form, but you really want to take a derivative in some unstable direction, for example, then my impression is that the best way would be to upgrade the transfer operator to the Grassmannian. Because if you look at it at the action on the Grassmannian, so you take also into account some derivative, some space on which you are taking the derivative, then the derivative becomes much nicer somewhat.
So not just one directional derivative, but 2, 3, 4-dimensional directional derivatives.
Yeah. I mean, that is, it could be more convenient. So, for example, if you look at, I have a paper with Sebastian Guzel in 2008 in Journal of Differential Geometry, in which we do that, and we show how you can use, because there the problem was that we wanted to use the Jacobian in the unstable direction as a potential, and that is very bad because it is only older. And doing this trick, we could have a potential that is smooth, but in this enlarged dynamic. I mean, we look at the dynamics extended to the Grassmannian, and over there we could write a nice potential that worked. It was cohomologous to the true one. So I think there are many different directions in which one can try to push this idea. The idea is very stupid. I mean, it's actually absurdly stupid. But I mean, it seems to me that it can be used in many different situations. So I wanted to just make a little bit of publicity to this silly thing.
Other questions?
Can I ask another question?
Of course.
In the, I'm familiar with I remember attending a mini course by Sebastian Guzel on how to get central limit theorems for dynamical systems using this idea of Guivarch, where you have parameter family of transfer operators. Does something like that, does this idea that you presented, does it help in that setting?
I do not think so, because you see, this works kind of nicely when essentially there is no potential, right? When there is a potential, you have to work much more, because you have a compact term that appear and is not obvious what to do exactly. When we can do, in our paper, we do some example in which we can do something, but it's more complicated. But in the case of this Givash approach, you just twist the transfer operator, putting some kind of exponential weight, complex exponential weight. But then the point is that you are interested only in the spectrum for the potential that is very small. Okay, so then this you do normally for biperturbation theory. So that is not, you don't need much. If you look, for example, at large deviation, then you may be interested in very large deviation. And then you may want to know the spectrum of the operator for potential that are large. There, maybe it could help, but I didn't think about it. I have no idea.